Welcome to this class on neuroscience of human movement. So, this is part 12 of our discussion on primary motor cortex. So, we have been discussing recently about lesions and how the motor map is dynamic, how plasticity can be helpful, or the possible role or possible exciting role of plasticity in improving brain function or improving motor function in people with compromised systems. Another way to help patients with neuromotor disorders is brain machine interfaces. So, if you go to neuroscience conferences, there is this regular neuroscience that gets discussed in the regular neuroscience sessions, and then you go to the neuroprosthetics nano symposium, for example, in Society for Neuroscience meetings, right. It is hot. It is that particular place that is absolutely glamorous. It is that place where these individuals are going to stand and listen to talks. It is that everywhere else there will be a lot of chairs that are free. In any other nano symposium or symposium, mini symposium, any other talks, there are going to be chairs that are going to be free, because not every so that room is designed for a larger audience, but usually just enough audience fill that rooms. But when it is neuroprosthetics, the room will be full, there will be people sitting on the floor and then there will be people standing on the floor. Why? Because this field is hot, super hot, right. The other topic of interest is of course neuroeconomics. I do not want to get into that. So, this topic is neuroprosthetics, and there are several components of this brain machine interfaces and how to perform signal analysis from brain machine interfaces. Fortunately, a substantial amount of progress has been made within prosthetics, not necessarily in the movement generation field, but in a different field. This is in the prosthesis of the auditory system, for example, cochlear implants. Substantial, in my limited view, in my humble view, or in my limited reading, I believe that cochlear implants or auditory prosthesis has made substantial progress within the neuroprosthetics field. Signal processing algorithms are very advanced. Instrumentation for measuring and for implanting and for stimulating are very advanced, are at a stage, and it is very already commercially successful when compared with other. For example, we compare this with other forms of prosthesis. What are the other forms of prosthesis? Movement related prosthesis, or for example, eye, relatively limited success, relatively limited commercial success, relatively limited establishment of algorithms and instrumentation. However, in cochlear implants there has been tremendous success. So, if we are to proceed, at least in my view, if we are to be successful in improving brain machine interfaces for movement, then we must learn the lessons from this field, from cochlear implants. So, but we are interested in this course on movements and improvement of movements. So, we will continue our discussion on how this can be achieved using brain machine interfaces. So, what is the goal? These are also called as neural control interfaces. So, the goal is to develop prosthetic devices, right. It is possible for a monkey, an animal, to be conditioned, right. This was shown earlier much long ago by Fetz and his colleagues, right. And it is also possible to come up with specific relationships between individual neuron or populations of neurons to particular movements. So, this particular movement is elicited by this population of neuron, and this particular for example, a population of neurons encode the direction in which the movement is going to happen. We saw this from the work of Apostolus Georgopoulos, for example, and there are other things. It is also possible for us to perform mental rotations, right? Mental rotations of the neuronal population vector, brilliant study. Those who are interested must check that. So, it is possible to change all these things. So, a question is, and a hot topic is, can I move or can I perform movement of a prosthetic limb or a robotic arm by mere thinking. So, I am thinking like I am going to move, and let us suppose some electrodes or recording electrodes are implanted in my brain, and they could record the activity and perform movements using a robotic arm. The answer is yes. Technology is available today to convert thoughts into actions, right. So, that is what this monkey is here is doing. So, here is the monkey that is seeing, right. It is seeing the activity. It is not the monkey's hand, you see, this is the robotic arm, this is the robotic arm, right. So, these are the robotic arms, right. So, the picking up of the treat, for example, is achieved by the monkey by mere thought, right. So, with some training, which this would give you the idea, wow, so this can be done so easily. No, there are several challenges along the way that have been overcome already before this monkey can actually achieve this, that are not presented in this picture. So, those challenges that have been overcome are the lessons that have been learnt, have not been discussed as part of this, but at least the main result, the core result is that it is possible to achieve what we want in terms of, but why do we want that? A question is, why do we need that? Does it even have any meaning? The answer is yes. There are individuals who cannot make movements, who cannot perform movements even to communicate. Movement system is completely compromised, and they live for relatively long periods nowadays because of improved medical care that is available. That is good, fortunately. Unfortunately, they will have to live with the disease. So, then the question, then the problem, that is challenge that is presented to us as scientists is, how do we improve their living conditions, or how do we improve their quality of life? If we can produce devices, that perform activities of daily living for these individuals, it is a huge step. What do I mean by activities of daily living? The basic activities such as buttoning up one's own shirt, or such as brushing one's own teeth, or such as grooming oneself, right. Things that healthy normal individuals would take for granted, but for these individuals, for individuals with compromised systems, it is a huge challenge, and it is also greatly depressing for them when somebody else, they have to depend on somebody else for drinking from a cup of water, and they have to depend on somebody else to come at a particular time so they can brush and comb and dress themselves. Huge difference. And by the way, there is also depression due to clinical factors. So, these individuals are having multiple problems. One is that they have a compromised system that is causing a deficit or a huge deficit in movements. The other is that this compromised system also causes clinical depression, and the fact that they are not able to perform even simple activities of daily living, they have to depend on somebody else to wash themselves or to use the restroom, has huge implications for their mental health. And these individuals are going to live, how do we improve their quality of life? What can we do? That is the question. So, to that extent, can we come up with devices which can provide them basic movements at least? For example, buttoning one's own shirt. Unfortunately, buttoning one's own shirt, trivial as it may seem, involves relatively complicated mechanics. It is not a trivial problem. It is not like you could button your shirts with trivial mechanics. The mechanics involved continues to be quite complicated. So, there are multiple challenges in this field. In the good old days, or the first approach towards this was towards achieving an acceptable prosthetic devices was performed mainly using EEG, non-invasive technique. Still being continued, it is a hot field, this is still being continued. And another approach was eye movements. Several challenges exist in these. For example, EEG, if you see, is the activity that is recorded at the scalp level, right. There are about 6 layers from where the recording is made to where the actual activity is originating. The activity, the neural activity is originating in the brain, but the recording is made at the scalp. There are several things we know what is between the scalp. There is scalp, skull, dura mater, pia mater, subarachnoid matter, cerebrospinal fluid, then the surface of the cortex, and then the activity may be deep. If it is too deep, then EEG may not be able to pick up. So, there are several challenges, yet advanced signal processing algorithms are available to classify these. But from these, can we perform relatively complicated movements? It is an open question. This is an open question. Similarly, with eye movements, there are multiple artifacts that could happen either with the EEG or with eye movements. Multiple challenges exist in terms of how to use this for real practical brain machine interfaces. So, that is a huge challenge. There are groups of people who are studying these and improving algorithms, improving instrumentation in these fields. But a hard field is the following: can we record directly from the cortex? There has been substantial improvement in the microelectrode technology. So, we could implant electrodes in the cortex and record population activity from multiple neurons, and then use relatively advanced algorithms that can extract signals about the exact motor intention. What do you want to do? It is not clear what the person wants to do. I mean, in a healthy person, that is clear. What the person wants to do, the person will do. After the person does what they want to do, that is what they wanted to do. In the individual with compromised system, they want to do something, but nobody knows what they want to do. So, the intention, decoding of that intention, he is the challenge, right. So, can we extract the motor intention from the signals that are recorded? That is one. Then this intention must somehow be converted into control signals that control mechanical interfaces, is it not? Control signals to generate particular movements by an external mechanical effector. And more, in the real system, in the intact system, we have feedback from the sensory system. What are these? We have said what these are. These are proprioceptors, cutaneous receptors, etc., that are sensed by the whose activity gives information about the external world to the primary somatosensory cortex. So, in these individuals, it is possible that the sensory area is also compromised. So, sensory feedback signals are very useful to improve performance. So, there must be two loops, one is sensing, the other is actuation. Both of this must happen. Relatively advanced algorithms are required. So, that is that. Here is an example system or a block diagram or a rough block diagram system. So, this is relatively early system, so about 15 years ago. So, the monkey's intentions are recorded. So, this is from implanted electrodes and from a relatively advanced data acquisition box. So, these are the challenges that we will have to overcome. The system that we make must be portable, must still be very effective and have high computational power, is it not? So, must be able to execute algorithms such as artificial neural networks and perform fits, maybe linear or non-linear as the case may be, and then make real time predictions that are then converted into actions by this robotic arm. This is multi degree of freedom robotic arm that is present, and this position and velocity is fed back to the monkey. So, the monkey is seeing what is being done and it wants to learn to move the actual robot arm. All this we want to happen, most important word, real time. Now, we have been somewhat successful in achieving this, but not super successful. There are still challenges challenges exist in reducing size, challenges exist in improving computational efficiency, challenges exist in instrumentation, challenges exist in signal processing. Most importantly, challenges exist in making these systems affordable. Unless this system is going to be useful to a relatively large number of people, these systems will continue to remain in scientific papers, but not necessarily in the hands of individuals. How do we make these systems affordable and help people? Are we doing this to why are we doing this? I would presume that we are doing this to help people. If we are doing this to help people, the goal is to make them affordable and practical and practically useful. So, it should not be so difficult that nobody wants to use it, nor it should be too simple that it has no practical application. So, that trade off, that sweet spot is difficult to achieve. That is the reason why there is less commercial success of these systems when compared with for example, cochlear implants. Cochlear implants are relatively successful commercially when compared with say movement prosthesis. Why? From time to time we see these exciting YouTube videos that show, oh, here is a robot that is moving by mere thinking. Yeah, those things are cool, but are these things being used by individuals who need it? Are these things commercially viable and sustainable as an option? That continues to be the question, and that is one area where people like us can contribute. So, in this class we have seen what is the brain machine interface and discuss some aspects of brain machine interface, what are the components and how to obtain neuronal signals, how is this obtained nowadays from implanted electrodes. By the way, with implanted electrodes there are challenges. Okay. So, with this we come to the end of this class. So, thank you very much.